Hello, and welcome back to Educator.com, and welcome back to physical chemistry. So today we're going to talk about the Schrodinger equation as an eigenvalue problem. So let's get started. Let's go ahead and work in black today. So now recall example 3 from the previous lesson. We had an operator which was, I believe, C hat, and we said that this operator was defined by minus I times h bar ddx of something, whatever f was. And we said that f was equal to e to the I times n times x. We operated on this, and we found that the c hat of our particular f was equal to n times h e to the I n x, e to the I n x. Now, notice that operating on f is the same as multiplying it by we just ended up, the original function was e to the I n x. The operated on function was nh times e to the I n x. We ended up just multiplying the original function by some scalar, by some number, positive or negative. It actually doesn't matter. So this is the general arrangement. Operating on f is equal to some scalar times f. Some scalar. Okay, so the only thing this operator did, so the only thing this particular operator did was multiply f by some constant. Was multiply f by some constant. In other words, if my function were x squared, I may have ended up with 17x squared. That's it. I just multiplied the x squared by a factor 17. That is all. Now recall example 4. In example 4, we had that the operator d was actually equal to the partial derivative of the function with respect to z. And in that particular case, our f was equal to x, y squared, and z cubed. In this particular case, the operation on f ended up equaling 3x y squared z squared. So here, operating on f didn't just multiply it by some factor, by some scalar factor. The d of f was 3x squared y squared z squared. Let's make sure this is clearly a 2. The original function was x y squared z cubed. So in this case, it didn't do that. Now, when an operator operates on a function and gives back the original function multiplied by some scalar, this is profoundly important. This is profoundly important. Here's where we're getting into some very, very deep and important mathematics.